Hello, everybody. I thought I'd do a discussion on an article that I read that I really like. One of the issues that we encounter when teaching statistics is the degrees of freedom and how do we actually explain degrees of freedom to students, but also tell them what it really means. And I think it's a struggle. So I found this great article by Joseph Lee Rodgers, who's from the Department of Psychology and Human Development at Vanderbilt. This was done in 2019. That's the best article I've ever read on degrees of freedom. It essentially takes degrees of freedom and treats them like money that one has in a bank account that one must withdraw in order to, well, actually, let me just put it. But let's just start with that. One has to withdraw in order to pay for estimating parameters. Okay. So if you imagine that we have a bank, and in that bank we have our money, but instead of money, instead of a dollar bill representing a unit of currency, $1, right? Instead of that, each participant is the equivalent of a dollar. So if I have one participant, I have $1, two participants, I have $2, and so on, right? So that's my currency. When I make estimations of population parameters, with in statistics, we seek to estimate population parameters using sample statistics. A population parameter is a fixed value, such as, say, a mean, like a population mean for something like, let's say, we're looking at the mean value for depressive symptoms among high school males. So our population, or what we call our sampling frame, is all high school males, and there's a mean depression or depressive symptoms for all high school males, right? So our goal in statistics is to get an estimate of that sample mean for whatever purpose we want. Like we may be trying to make a prediction of depression based on something like that, whether or not somebody vapes or something like that. So we're trying to get estimates of these population parameters. Population parameter can be the mean, it could be something else, could be a variance, could be a regression coefficient. So I'll play around with the idea of a regression coefficient. I think he has, I'll be describing that, but I think that there are some equations in here that will be helpful. I'm pretty sure. Yeah, like here, let's see. Yeah, here's an example. Okay, here's an example of a regression equation where we're trying to predict an outcome value, and in this case, our outcome is Y, and it could be something like depressive symptoms. And if we don't have any predictors, so here's an example of a regression model where we have a predictor. A regression model, whether it's simple or linear, but let's play with simple regression. Simple regression means there's one predictor and one outcome. Is a line, right? The line has an outcome, right? This is a point on, if we look at axes, we have a y-axis and an x-axis. This is a point on the y-axis. There's an intercept where the line crosses the y-axis. In this case, and generally we use b sort of convention to represent what we call population parameters. In this case, the intercept would be a population value, but we're trying to estimate it. So that's one. And then you have the relation between the predictor variable and the outcome. So if our predictor is something like vaping, this b here would represent the slope. So a line has an intercept and a slope. And I think I think there's a picture here. I think he has some nice graphs that we can look at. If I go down the line here, there you go. So here, like here's an example where you have a y-axis and an x-axis, and then points are being plotted on this line. All right, so let's play with this for a second here. So my goal is to get an estimate of this line. Like I'm trying to make a prediction of depressive symptoms based on vaping. So we have zero. Well, let's do vaping in the past 30 days. Zero means you did not vape in the past 30 days, and one means you did vape in the past 30 days. So for each participant, we gather their depressive symptom value, and then we get their value on vaping. And then we're going to try to formulate a relation between the two variables. But first, he starts by showing you what if we're just trying to estimate depressive symptoms without any predictor variable. So in that case, the best predictor of our outcome is the mean. And this is a mu value. Mu is a Greek letter. Greek letters represent population parameters. This would be like a fixed value here, which we'll estimate with some kind of a sample statistic. So in this case, the b sub 0 is the sample statistic. And when we estimate this value, we're going to be off by some amount, right? Because we're never going to be perfect in our estimation. And that amount is our error term. So that's why you have, in this case, you have y. So let's say y is the participant's depressive symptoms. This is the population mean, and this is the difference between the actual value of the outcome variable, in this case, depressive symptoms, and the predictor. And there is no predictor, so we're just using the mean as our model. So our model is the mean in this case, right? So we need to estimate that mean. So let's say I'm going to use 50 because they have 50 here. Now, I'm not going to go over everything because you can read the paper on your own for the rest, but I'm going to get over the most important part of all. So let's say I have 50 individuals, right? I've collected data on 50 individuals. So basically what I have is $50 in my bank. Again, one individual represents $1. So my data bank includes $50. But I need to estimate this population mean for this model to work, right? I need this b sub 0. So to estimate that b sub 0, I'm going to pull $1 out because it's going to cost me $1 in order to estimate that. So where I started out with $50, or would we say 50 degrees of freedom? Is that, well, why degrees of freedom? Because those values those 50 individuals can be any value possible, right? Right. So now we're going to take one of them and we're going to fix them to be our population mean value. We're going to take one of those values, and whatever that value is, so let's say it's 20, then our population mean can be 20, right? Or let's say it's 17, another one is 17, pull that one out, and that one would be our estimate of our population mean, right? So we're pulling one of those out so that we're losing 1 degree of freedom. We spend $1 basically, right, in order to make that estimation. So now we have, instead of $50, we have $49 left. It costs us a unit of currency, or $1, or a degree of freedom, if you will, in order to make that estimation, right? So now we have 49 left, right? It's like how many bottles of beer in the wall? Take one down. It's making me think of that. The next step would be to start making the estimation using our predictor variable. In this case, our predictor variable was vaping. Right? We want to see what's the effect of vaping on depressive symptoms. This participant could have a 0 or a 1 for this value. So we need to estimate the relation between the two, right? The relation between the two. And that's going to be indicated by the slope. I'm not going to go into how to calculate that slope in a simple linear regression. I probably have a video showing you. I know I have a video showing you how to do that somewhere else. But anyway, we're making that estimate. So now we need to withdraw another $1 from this data bank, right? So we're going to use another individual basically to calculate that. So now we have spent 2 degrees of freedom in order to calculate these two statistics to estimate those two population parameters. So then we have $48 left in the bank. So a couple of things about that. So we've used 2. It means we have 48 left. What are we going to do with those 48? So now we can do a lot of other stuff, and we can continue to estimate additional slopes, right? Additional parameters here. To estimate additional parameters, slopes. We can, I don't know, we can calculate our R squared, the proportion of variance accounted for by the model. We can do a lot of different things. There's a lot that we can do with that. We can do all kinds of model testing, et cetera. We can just do a lot more because we have some leftover degrees of freedom. So again, there's other issues involved here too, but that's not the purpose of this. I mean, you can read the article for that, talking about, for instance, just identified, et cetera, or over-identified or under-identified. But the point here is to look at degrees of freedom. It's interesting, though, that when I read about degrees of freedom in most articles and things that I've written too in textbooks, we generally talk about, well, degrees of freedom is you lose freedom when you make an estimation of somebody. We use like a clever little example. A colleague of mine did this herself. He used like an example, say, okay, well, imagine that you have three people and three candy bars, right? The first person has three choices of candy bars. Take one. Then the second person has two choices. The last person has no choice left, right? That's a good way to explain degrees of freedom, but it doesn't really say what it is. And I didn't say why you do it either. No, I just started explaining using economic terms or banking terms how we would actually calculate degrees of freedom. Now, here's an interesting example where you plot. So this is looking at parental supervision and adult drug use. So there's one data point, so $1. It's only $1 deposited in the bank. It could be, I mean, that's all we've done so far is just to have this one value. If we want to like calculate the mean, and we were always focusing on the outcome variable, not the predictor variable. So like we're looking at adolescent drug use, we'd use that one value to predict adolescent drug use. So we have one value to predict, one parameter to estimate, and one value to use. So we have no additional degrees of freedom. We've used them all. So 1 minus 1 is 0 in that case. And this author here shows like what happens if we have two different participants. Now with the two participants, I can actually draw a line, right? I could draw a line and say estimate the relation between the two with a line, because I couldn't do that with 1 point, right? But I could do that. I mean, with 1 point, you could have a whole bunch of different lines crossing through here, right? But here, there's only one line that crosses through this. If I have two data points and a line has an intercept and a slope, two parameters to estimate. I have two data points and two parameters. I'm still what's called just identified. I have just enough information to fulfill my needs. But if I have a lot of points and I want to predict a line that has the intercept and slope, it's a better situation because now I could plot a whole bunch of different lines here, right? This one, there's only one line. And the key point, what he was showing here was that, so in this case, we're over-identified. We have more data than we have points to estimate. Like we have here, if it's 50, we have 50 data points. And we only need the intercept and a slope. So we can draw a whole bunch of different lines. We don't know which is the best fitting line here, right? In this case, it was this y equals minus 1.6 x. This is your slope, negative slope, and then here's your intercept, right? But I could draw other lines and I could challenge whether or not this is the best line. The moral there is the more data points you have, the more different models you can propose. So that's another benefit of having a lot of degrees of freedom left over. It's because with more degrees of freedom I have, I can propose competing models and compare the two and see which one is better. That still doesn't tell me why we have to do that, because sometimes I think, if I'm doing a t-test, like, well, where do we use degrees of freedom? Like in t-tests, right? Like if we're comparing two independent samples or comparing a sample to a population when we don't have the population standard deviation, or we're comparing pre and post on something, right? Two repeated measures, right? So we lose a degree of freedom, right? So there's different, of course, when we're doing independent samples, t-test compared to independent samples, there's different equations depending on whether or not we can assume equality of variance. There's different equations, but let's say we can assume equality of variance, it's n1 plus, sample size for each group minus 2, because we're estimating two means, right? So we lose 2 degrees of freedom in that case. So degrees of freedom play a role in t-tests. They also play a role in the chi-square test, where they're related to the number of rows and columns, right? Because we're estimating row totals and column totals, and how many values do we need to estimate those, right? Lose one every time we estimate one of those values. Because if we have three different, say we have never smoker, smoker, a current smoker, and heavy smoke, three different levels, right? Current smoker, moderate, and heavy. So we have three different cell values to estimate, and they have to equal the total. So we need two out of three. So we'll lose a degree of freedom because there's one of those is fixed, one of those is a fixed value. So we use it in chi-square as well. And then F tests, we use those there too. But what they do is they determine the shape of the distribution, right? So you have a different distribution depending on the number of degrees of freedom. And degrees of freedom for t-test is equivalent to talking about sample size, right? Basically, because you're losing like n-1 or n-2. If you have 1,000 people, right? It's very little difference between the two. If you have 20, it's 20 minus 2 is 18, right? So it's pretty similar. So the degrees of freedom determine the shape of the distribution, right? So that's one reason they're critical. So we need that. What you can say, well, do we really need to, if I have 30 people, it's going to make a difference. If it's 30 versus 29, test it out and see, look at the difference. But it could play a role here and there, depending on how large your sample size is. So that really the reason we look at degrees of freedom is because they change the nature of our distributions, and those distributions dictate what our probability values are, right? If you recall using the Z distribution, a standard normal distribution, just called a standard normal distribution, we know all the probabilities for any range of values, right? What's the probability being greater than two standard deviations above the mean, and so on and so on, right? We know everything about that distribution. So if the distribution is changing depending on the degrees of freedom, we need to know the degrees of freedom. And then also, I have this one video, so I'm going to go to my YouTube channel here. I have this one video here in my YouTube channel that also shows you, here's an example of where we lose a degree of freedom when we're estimating the population variance from the sample variance. This is the population variance would be sigma squared in this case. And we're estimating the right, we're making an estimate of the population variance using sample variance. And our denominator is n-1, right? So okay, it's because we lose a degree of freedom. True, but if you were to, in order for this, we always talk about how the sample variance is an unbiased estimate of the population variance. To prove that, if we don't divide by n-1, it wouldn't work, right? It wouldn't work. So losing that degree of freedom there is critical. And you should watch this video, why we divide the sample variance by n-1. And I can show you, it just works out mathematically that if you don't divide by, or see here, I pulled it out, it's constant. If you don't divide by n-1, we could not claim that the sample variance is an unbiased estimate of the population variance. So the answers basically to these questions are not very, very clear and just I mean, they're I guess you could say they're intuitive, but they're not necessarily made explicit by every textbook author. Why? I don't know. I mean, it's a lot of work to do this. And as you can see, even me explaining it here, it's not the simplest thing to explain because there's like lots of little, it's like when I cycle and I have to climb all these hills, I think I'm over a hill and then all of a sudden there's another hill. So you get all these little hills and valleys that you have to climb through to make sure that people understand it. But it is key. So yes, it is justifiable to account for degrees of freedom. And I think we should all be able to explain it when we're working with students, including me. All right. Thank you, guys.